Boston Dynamics 发表电动人形机器人 Atlas。在 Boston Dynamics 所公布的电动 Atlas 影片中，画面一开始时，电动 Atlas 是躺在地上的，但它以人类无法办到的方式起身及转换方向，最后看住镜头后仰长而去。这时候你看到了什么？也许未来有一天，机器人大军将会影响到你的生活，甚至你的生命。接着，让我们
This video should in many ways look familiar to those who've seen our videos in the past, but it's meant to communicate an expansion of the research that we're doing on Atlas. So we're not just thinking about how to make the robot move dynamically through its environment like we did in parkour and dance. Now we're starting to put Atlas to work and think about how the robot should be able to perceive and manipulate objects in its environment while maintaining that characteristic high level of performance that we expect from Atlas. In order to do that, the robot has to be able to think about the properties of objects, their shape, their mass properties, and as it's manipulating these objects, the constraints that exist between the robot and the object, the forces that exist. And it has to have a control system that's able to balance what may be competing objectives related to stability or the manipulation task at hand.
My role in the project was working on perception and autonomy. So perception is letting the robot know what it's seeing, and autonomy is letting it choose what it's doing next at a high level, where it's going to go and what it's planning to do. It's all software, so we're writing code that runs on board Atlas, and it's got computers on board that are processing the camera data so that it can see the objects in front of it. In this video, we're doing a lot of object manipulation, lifting this piece of wood, placing it down, lifting up the tool bag, and eventually jumping and trying to throw it precisely up onto the top left.
So Atlas has a couple of cameras that we use to see the world around it, and they work not entirely unlike a human with eyeballs. So we can see the colors of things around us, and we can get some information about how far they are away. We use that to build models of the environment. So we might know that we're going to be running over a sequence of boxes, and so we see some box-like shapes out in front of us. We decide, oh, those are probably boxes, and we go and we decide to run on top of each of those boxes. And that works really well when the environment looks something like what we're expecting.
The Atlas perception system works with the cameras that are in the head. It has a color camera and has another camera called a depth camera. So this uses photons, time of flight, to measure the distances to everything that it can see. We basically are looking for shapes in the environment and other features in the environment that Atlas can use to identify key objects of interest. So I was going to put it down. And then the next thing it's going to go do is go look for the bag. So it's been told the bag is somewhere over here, and now it's got to turn. And right after that turn, the bag is now in the view out here in the distance. And so it's going to start estimating the pose of the bag. You can see there it's found it, and it's sort of thinking about the shape of the bag and how it wants to grasp it like that. And then it comes in, and we get a nice view in the front camera here of the grippers making the grasp around the bag like that.
So the way that we approach this problem is a technique called model predictive control. And the idea is that the robot's control system should be able to think about how its motion is going to evolve in time in a way that respects the physical laws of our universe. So for example, if you're imagining the robot's holding a heavy object while trying to run, or pushing something that weighs on the order of its body mass across the room, carefully considering the forces that exist between the robot and the object and how that might or might not tip the robot over, for example, is really important to success.
So a predictive controller is a way of doing controls by thinking about what's going to happen in the future. And a really simple example is that when you stand up as a person, your heart has to pump harder to make sure you have enough blood pressure to do that. And in fact, if you look at people's heart rates, they go up before they start standing up. So your body is sort of thinking about what is my heart going to need to do now so that in half a second I'm ready to be standing. And the robot's doing exactly the same thing. So it's thinking about how hard do I need to push with my right foot so that 1 second from now I'm not falling over.
My role in this project was to basically take the controller that we had before we started this manipulation effort and extend it so that explicitly thinks about the object that it's holding. So it has an explicit model of the object and its interaction with the robot. So we're interested in manipulating very heavy objects, so inertially significant in a sense, which means that actually thinking about the forces acting on the object, and action equals minus reaction, the forces that the object exerts on the robot also becomes very important.
I think one of the hardest things about grabbing an object and moving it around with the robot is that it creates an entirely new set of problems of trying to decide where is this object that I'm manipulating and how is it moving. It's already hard for a robot to know where it is. So when we're trying to manipulate something like a plank, we have to just make pretty educated guesses about where is the plank, how fast is it moving, how do we need to move the arms to cause the plank to spin 180 degrees very quickly. And if we get those estimates wrong, we end up doing silly things and falling over.
So we're unable to read the encoder, the position encoder for our elbow or shoulder X, we call that. It's when the robot lifts its arm up like this. So we can't command it if it doesn't know where it's at. And sometimes sensors will break, cables will unplug. And so we're doing a really fast diagnosis to figure out what's happening. I am the electrical tech, Atlas's electrical doctor. And these other two folks here, Bill and Crystal, they're both partially electrical and very mechanical tech. So right now they're checking in on the wiring, and I'm watching to see if there's any signs of life as we go through and see if maybe we have a loose connection. Or maybe we have a dead sensor.
They use similar hydraulic systems in like a Formula One car, essentially, and they would, every event, they would take everything down and probably replace the seals, I'm assuming. And the difference is they know what the use case is. Where here, they're doing new things pretty much every time they run. They're trying new movements that might overextend an arm or a leg or collide with another part of the robot.
So everything Atlas does in the real world, we developed in simulation first. The simulator is sort of like a video game. It's a virtual world, and Atlas can run around in that world, and we can test a lot of variations of the behavior before we run it in the real world. It helps us understand the limits of what the robot can do. You know, can it jump even farther? Can it jump even higher? We can explore all of those questions in the simulator, and then we can test them on the real hardware. And often those tests in the real world will result in a broken robot, which is fine, we can fix it. But if we want to push the boundaries, we can do that in sim first.
Yeah, one of the main things I've worked on in this production, that's been the final jump. So we have a jump where it's doing a flip in the air. So previously we've done one axis flips. So we've done a back flip that goes only on one axis. And right now, with this new jump, it spins around multiple axes. But one of the big challenges here has been that we're working at the very limit of the robot. So we've had to do a lot of changes to the controller. And basically, we wouldn't have been able to do this kind of jump just 1 year ago.
This is the robot squeezing its limbs in the same way that a figure skater would tuck their arms in to spin faster. So it's actually trying to become as small as possible to spin really, really fast to get all the way around.
So the move you're seeing at the end we refer to internally as the sick trick. That's kind of our code name for it. I hope the world thinks it's as sick as we do.
It's a flip with a bunch of spins. I think it's something like an inverted 540. The robot is starting facing out, and then it spins, and when it lands, it's facing back at its takeoff box. It was a very cool move, and it took a lot of work to get that to land cleanly. It certainly inspires people to say, what if we could make a robot that can do this? And we can start exploring those questions first with Atlas. And if something seems to be working really well, or we see some application in it, we can develop that technology further and move it into our products that are actually going out and operating in the real world.
Well, the dream of humanoids is that they should be able to do all the things that we do, right? A humanoid robot will be well suited for applications like manufacturing, factory work, construction, where a humanoid form factor actually fits very well with its bimanual nature, its ability to stand upright, move heavy things around, and work in spaces that were traditionally designed for humans to do work in.
I think what we're focusing right now for real-world applications for this kind of robot, things like moving objects that are pretty heavy, especially in environments where it's either too dangerous for humans or where it's just generally something people don't want to be doing. I really want to see robots helping out in disaster response scenarios. I want to see robots moving around in the world in ways that allow humans to do things that are better and safer and happier with their lives.
Forgot my tools again. Such a show off.
My name's Josh. I've been at Boston Dynamics about 4 years now. I'm a mechanical engineer on the Atlas team. I think what first got me interested in high school, I built a drone, a little quadcopter, and it was absolutely terrible. It could barely fly, but we did everything. We did all the software, the electronics, and just going through the process of seeing how we're tuning variables and it's responding to inputs and trying to stabilize was truly empowering. And I think from there, I just felt, a desire to do more. And in college, I kept on learning and building more robots, did all the projects I could, and eventually that led to working here. Mechanical engineer, we design all the physical parts on the robot, the arms and the legs, structures, the motors and actuation, batteries, anything on the robot that's physical, and you can see that that's where we specialize. We also do a lot of analysis and math to make sure that the robot will work, that the joints are strong enough, that if it face plants while doing a backflip, things aren't going to break and fall apart. It kind of goes through phases. Some weeks we're doing a lot of testing and we're breaking robots intentionally or unintentionally, testing mechanisms if they perform the way we expect to. Other weeks are really design heavy, and like everyone here, we coordinate a lot with other teams and disciplines, electrical engineers, software engineers, to make sure that the robot will work well. So how do you build a robot? So yeah, for the robots here in Boston Dynamics, we really have to approach it from a systems level. You can't sort of design each part individually in a bubble. It'll never work that way. You can think of it sort of as a picture coming into focus where there's a lot of blurred lines and things don't have much definition, but we're trying to think about everything holistically. And then throughout stages, we're detailing out parts kind of in parallel at the same time. So we take all these people and as we're building the robot, everyone's voicing concerns, contributing, and then kind of through that large team effort, you end up with a robot. The smartest person in the room, and that's the best place to be. There's always so much to learn. What does Atlas do? That question gets asked a lot. So Atlas is our R&D robot, our research and development robot. And you can think of it sort of as a technology demonstrator. So we're really trying to push the limits of hardware and software and controls with Atlas, thinking about years and years into the future and how we can learn from that technology and spread it to all of our robots. How fast can Atlas go? So the fastest we've gotten it to go in lab is about 2.5 meters per second. It's about 5.5 miles per hour. But there's sort of this running joke around here, how we keep on thinking we've capped out the robot, and then the software team develops some new behavior that is more athletic and coordinated than anything we've done before. So we think there's quite a long ways to go before we've capped out the hardware. What was the first prototype of Atlas? So the first prototype was way before my time. It was called Pet Proto. It was actually our robot Big Dog, which you may have seen. It's one of the classic ones where we kick it and stabilizes. It was that robot. We just took 2 legs from it and stood it on its hind legs, and then we attached 2 arms to it. And that was the predecessor to our first full humanoid robot called Petman. And then that led to over a decade of development and iteration to the robot you see nowadays, which we refer to as HD internally, which is humanoid version D. And that's what you see on our YouTube videos doing the parkour. What hardware do you specifically focus on? So on Atlas, that robot was more or less finished by the time I got here. So I just did a few upgrades. We upgraded the battery. So working on how that battery gets installed and the roll cage that protects that. On stretch, I focused on the distal arm, which is the end of the robot by the wrist, and the gripper as well. How does manufacturing differ between robots? It's a good question. So we have a really broad range of manufacturing here at the company. So on Atlas, we design a lot of metal 3D printed parts that are super lightweight and very, very strong and stiff. Whereas on Stretch and Spot, we're designing for very specific processes that scale well towards production. Apart from software and electronics, how much of mechanics is needed to study to approach robotics? Nowadays, robotics is super approachable from all majors. You don't kind of have to know everything in every field to do robotics, which is really exciting because it didn't used to be that way. If you're really interested in software, you can buy pre-built kits that let you spend 95% of your time coding, and you don't have to worry about the mechanisms. And likewise, if you're really into machining and designing parts, there's a lot of microcontrollers that make programming really simple, and then you can focus on building cool machines. There's a lot you can still do to interact with robots without an engineering degree. So the applications of robotics are only getting larger every single year, and there's a lot of roles where you can introduce robotics into new fields. How can I get started with robots? There's a ton of ways to get started with robotics nowadays. In most schools, there's now robotics programs. A lot of the principles there really truly apply to the types of things we do here. If you don't have access to that, or really even in general, I would encourage you just to take apart everything that your parents won't be sad if it gets destroyed. If you get excited about it and if you're learning, you're doing the right thing. So just keep on going down that path. But a lot of people here, that's kind of the path that we took. We fell in love with robotics. We do it more. We're learning as we're going, and eventually that leads to doing exciting work here.